So the sinc function is simply sin x over x. So we can integrate this sin x over x over all x. So seeing the sine, we think, okay, well, we'll take the imaginary part of e to the ix. Now the problem with this is that this integral here is well behaved. When x goes to 0, sin x over x tends to 1. So there's no problem that x equals 0. Now the problem with this integral is actually it doesn't exist in the way I've written it, because when x goes to 0, this is 1 and we've got 1 over 0. But this is an example of when we can instead use the principal value and then we can do something with it. So we need to use the principal value and then this is fine. So there will be a pole, a simple pole at x equals 0. This type of integral we recognize as needing a semicircular contour. So we consider the limit as r goes to infinity of e to the I z dz over z. And the contour we want is this one. But this function here, e to the I z over z, has a simple pole at z equals 0. And the contour we're going to use is a semicircular contour which is indented at z equals 0. So it just goes around at z equals 0. E to the I z has no singularities in the complex plane. So the only singularity anywhere is this one here at the origin. So we know that this will end up being equal to I pi times the residue at this pole here. So if we work out what this is. Now along here, integrating, if we take the limit as r goes to infinity, integrating basically through a simple pole gives us the principal value. So this is precisely this integral here that we're getting. And then we've got the semicircle bit. I'll just write it like this, which we can say goes by, always draw the limit as r goes to infinity, which tends to 0 by Jordan's lemma. So Jordan's lemma, remember, says that if the function multiplying e to the iz goes to 0 as fast as or faster than 1 over z, then we're okay. The integral will tend to 0. So this integral here is equal to I pi, or this quantity here, which is equal to this integral here, is equal to I pi times the residue of e to the I z over z at z equals 0. And that is, well, when z equals, if you do p over q dashed, then we just get p over 1. When z equals 0, we just get 1. So this is actually just the residue is just equal to 1, which means that our integral is the imaginary part of this integral. Imaginary part of I pi is just pi. So just to add, we've shown this using the residue theorem. If we take real and imaginary parts, well, we've already taken the imaginary part of both sides and got this, the result we wanted. What happens if we take the real part? Well, the real part will give us cos x over x equals 0. Now, if I didn't have the principal value, then this integral wouldn't exist because I've got 1 over infinity at x equals 0. But the principal value does exist, and it's sort of what you expect. This is odd function you're integrating over all x, so you expect it to be 0.